In this first question, this is about verdigris. Verdigris is a green pigment. It contains copper-2 carbonate and also copper-2 hydroxide in various amount. So both of these compounds react with dilute HCl. As we know it, carbonate reacts with HCl to give us the salt. It started with copper-2 carbonate. So this is copper-2 chloride, CO2 and water. The hydroxide also reacts with HCl in a neutralization reaction. So this is copper-2 chloride and H2O. So you have to plan an experiment. So you got to plan an experiment to determine the percentage of copper-2 carbonate. So we do not want the percentage of copper-2 hydroxide. We want the percentage of copper-2 carbonate. However, they already told you that there's copper-2 carbonate and there's copper-2 hydroxide in varying amount. So you're going to use excess dilute HCl. So that is one thing you have to keep in mind. So the excess dilute HCl will react with both the copper hydroxide, copper-2 hydroxide, and also the copper-2 carbonate present in your green pigment. So this is what we have. We started with 0.5 gram of verdigris. We have that 10 mole per dm cube. So that is quite, it's not like super concentrated. That will be like around 18-20 mole per dm cube. But 10 mole per dm cube is still a lot more concentrated than, I don't know, the one you usually use for qualitative analysis is always like around 1 mole per dm cube, 2 mole per dm cube, that kind of thing. Yeah? You have commonly available laboratory reagents and equipment as well. So we are going to assume that verdigris is unaffected by heating, just in case we need to heat it. It is not acidic or basic. So why is titration not a suitable method? Okay, so we're going to react it with acid and then do a series of experiments, right? So why is titration not a suitable method? So your aim here is to find a percentage of copper-2 carbonate, but then you have both of these reacting with acid, right? So both this and this can react with the acid. So they are not going to, the amount of acid you get from titration is not going to tell you the percentage of one thing. It's going to be all of these that can react with the HCl. Okay, so that's why it's not suitable just to work out the percentage of one thing, which is what you want. All right, so both the copper-2 carbonate and the copper-2 hydroxide react with the dilute HCl shown in both the equations, above. Okay, so you won't be able to tell just the percentage of copper-2 carbonate alone. All right, so it is not just the copper-2 carbonate that reacts. Therefore, you can't just determine the percentage of copper-2 carbonate just by doing the titration. All right. So that 10 mole per dm cube HCl is corrosive, too concentrated. So this is going to be about dilution. We are taking a more concentrated solution and we are going to dilute it up to 250 cm cube, 0.500 mole per dm cube. We know this is 10 mole per dm cube, but we don't know what volume is required. So when we take it out from the 10 mole per dm cube, well, when we take out a specific volume of this 10 mole per dm cube, we just add distilled water. We don't just add water, we add distilled water for dilution to add out to 250 cm cube. Our mole is going to be the same because that is the whole aim of dilution. You keep the mole the same, but the concentration is going to be different. This is going to be more concentrated. This is going to be diluted. That's the whole point of dilution. All right. So you gotta work out what is the amount that you need to. You gotta work out how much of this first, right? Okay. Otherwise, you won't be able to complete the dilution. So we know the mole is the same. So 10.0 times the volume of the concentrated times 10 to the minus 3 because I want the volume of the concentrated HCl in cm cube. That is equal to 250 cm cube times 10 to the minus 3 times the new concentration. Okay, because it's calculation, I guess it's better if I do this. The volume of the concentrated HCl that I need would be 250 times 10 to the minus 3 times 0.500 divided by 10.0 times 10 to the minus 3. So I need 12.5 cm cube. So that's what my calculator showed me is 12.5. But you will know better that we will need a burette. So use a 50.00 cm cube burette. So burette is accurate up to 2 decimal place. They want any apparatus including their capacity in cm cube. So I'm just doing whatever they say here to measure out 12.5, well, hang on, 12.50 because the burette is accurate up to 2 decimal place to plus or minus 0.05, as you will know from your practical classes. And after having done paper 3, of course, which is your practical experiments, of the 10.0 mole per dm cube HCl equals, so there's the more concentrated HCl, into a, so you want to make out to 250, right? So you need a 250.0 cm cube volumetric flask. So volumetric flask is not just 250 cm cube, I guess. We always think about 250.0 cm cube volumetric flask. And then what you're going to do then is add distilled water. We don't want to add tap water. We don't just want to add water. We have to specify distill. Either you specify distill or you specify deionize. They basically say the same thing, which is basically the water doesn't contain any dissolved minerals. The water does not contain any dissolved ions. It's just pure H2O. Right, so add distilled water to make up to the 250.0 cm cube mark. And then you got a stopper the flask, and then you gotta shake to mix well because you want to get a uniform concentration. So when you make out a solution, make sure you stopper and you shake in order to mix well. Yeah. Next bit, so you gotta identify a dependent variable. So y-axis is your dependent variable. If you watch my other paper 5 tutorial video, you know that I keep on referring to this good friend of mine, a colleague. So she taught me this phrasing. Why are you so dependent? So y-axis is the dependent variable. It is what you measure, okay? Or you can get it from what you calculate based on what you measure. But it's something to do with what you measure instead of what you are changing, all right? What could you measure? What could you measure to determine the percentage of copper to carbonate? Earlier, they told you that just reacting with HCl via titration would not tell you specifically the amount of copper to carbonate because this can also react. But the only difference here really is the CO2 gas being given out. So this doesn't give out the CO2 gas. So if we measure the volume of CO2 gas, that actually tells us the amount of copper to carbonate, right? Because this is the only reaction. This is the only one of the two products that give off the carbon dioxide gas. This one doesn't give off gas. So we could be looking at measuring the volume of the carbon dioxide gas produced. Measure the volume of the gas. You can specify CO2, of course. Produced by the copper to carbonate reacting with the HCl aqueous. All right. Of course, we could, based on the difference, and I did mention it to you. I was gonna say based on the difference in mass, but that's gonna be tricky because this is also solid and solid. So your difference in mass is going to this is going to decrease in mass as well together with this. So that is not probably the best option. I'm still going for the production of the gas. That's the main difference between the two reactions, yeah? So now you have to draw a diagram to show how would you measure the dependent variable, basically the volume of gas. This is typically gas collection. So you have done gas collection in GCSE and O-level. When you were 14 to 16 years old, we talk about thermal decomposition. You need to collect gas. This is a carbonic acid reaction. You need to collect gas. Sometimes you have thermal cracking or catalytic cracking. You need to collect the gas, which you can do, either using a gas syringe, or you collect over water, or you collect over acid, or you collect over base, depending on the properties of the substance, or whether you want it dry, or whether you want it neutralized, etc., etc. A lot of different options, yeah? So this is just a carbonate. I'm just going to draw a very simple diagram. I'm not a terribly good artist. In fact, not an artist at all. Okay, so we need a rubber bunk as stopper. Okay, because you don't want the gas to escape. You would have the solid. You would have the what's the name of the compound again? Verdigris. Okay, verdigris. And then you will have the dilute HCl aqueous. And then on the side, you will have the gas syringe. So you have got a gas syringe. And because you're having a gas syringe, it's not just a gas syringe, because specifically we say we want to measure. Okay, so look at that term there, measure. Gas syringe just collect the gas, but this has to be, it has to come with this thing, what we call like graduated lines. All right, so that is your graduated gas syringe, meaning to say it's got these graduated lines telling you the volume of the gas being collected. As the gas gets produced, it will push on the piston, push. As more and more gas being produced, when the piston stop moving, there's no more gas that's being produced, as you'll be able to tell by normal bubbles being normal effervescence or normal bubbles due to all the carbonate having reacted anyway. Okay, that's it really. So how many marks is that? That's for 2 marks. It's pretty generous, I guess, having all the apparatus. So we already set out the apparatus, we put in the chemicals, we measure the volume of gas, and we label our diagram. That's it really. Make sure you have a stopper, otherwise your gas will escape and you're not measuring the correct volume of gas then. Okay, next bit. We got to sketch a graph how the dependent variable you identified would change. All right. So sketch a graph. Your dependent variable is the volume. So volume of gas, or you can say CO2 produced. All right. I'll imagine this would be in cm cube. And then on the x-axis, what are you changing? All right. What are we changing? In this experiment, we are measuring the volume of the gas produced over a period of time. So there will be time there, and we can measure time in seconds or in minutes. If I just put it down in seconds, so at every time, regular time intervals, we're going to monitor the volume of gas produced in the gas syringe, and then we will expect there at time 0, that mean you have nothing being added, and then you would eventually come to let me just show it better. Okay, so what I was going to show you is you would eventually come to a flat line, as I mentioned, when there's no more effervescence being shown by your solution mixture, and then there'll be no more gas being produced, therefore they won't push the piston further, therefore at that time intervals your piston wouldn't have moved, your volume of gas would have just stayed constant. That indicates that no more carbon dioxide is being produced, no more carbonate is present, because you use excess acid anyway. If you read all the way to the early question, you use excess acid. That's why you're supposed to read through the whole thing before you start doing paper 5. It's one of the things that examiners highlight every single year. every single exam session, they said that students should have read through all the instructions before studying. You might take a couple more minutes to read through the instructions and all the background information, but eventually it's gonna come back and help you after that, instead of you having to go back and forth to look at information every single time. Understand the experiment, understand what it is that this person has done or what are you supposed to do, then you might be able to suggest something better or think about, I remember reading through that, yeah? So up next, you have a student carrying out this experiment once. How can you ensure the results are as accurate as possible? So in order to, so this is not about reliability, okay? Be very careful, yeah? So sometimes they will say as reliable as possible, okay? So if they say that, then you need to do repeat. You repeat experiment until you get consistent results. Here, they specifically mention as accurate as possible, okay? So as accurate as possible means that you want accuracy. You don't talk about repeating, because repeating the experiment simply ensure reliability. It does not ensure accuracy, all right? This experiment is about volume of gas being collected. So being accurate means your volume of gas has to be accurate. So avoid loss of gas by ensuring everything is airtight, such as your rubber bunk. Make sure that it's airtight, okay? And so by ensuring the rubber bunk, basically the stopper on the flask, is airtight to avoid the loss of gas. All right, so remember that there's no gas being produced until we add in the solid, so we gotta be very quick. All right, so as soon as verdigris, which is the solid containing both the carbonate and the hydroxide, is added, immediately stopper the flask, because you want to prevent the loss of gas and swirl to ensure. So we swirl around, so we don't like shake them, because you know the stopper is not permanently fixated. We swirl to ensure the solid reacts. I guess the last part is not that important really, but I guess the idea is really loss of gas, airtight, stopper the flask after you add in the solid straight away, so you don't like let it linger around, otherwise your gas will escape. Yeah? So now in this question, a student suspected their 0.5 gram sample verdigris only contain copper 2 carbonate. Okay, only, okay? So suppose that if it only contain copper 2 carbonate, then if the student was correct, what is the minimum volume of HCl required? Well, they give you the MR of CuCO3. If we just look back at the original equation, they're saying that only copper 2 carbonate exists in the mixture, so we don't have this competing reaction. So therefore, the mole of copper 2 carbonate over the mole of HCl is just 1:2. Does it matter if you have it the other way around? Does not matter at all, because you would have known in my other tutorial video. As long as we set up mole ratio like this, if you got it the other way around, then you have 2/1. And then we will have set up on the right hand side the actual mole correctly, based on whatever is on top and based on whatever is at the bottom. And you wouldn't be wrong, because you know how to read your own handwriting, and you know how to read your own data, okay? So that was from the balance equation, as I've copied from up there. Maybe I can move it up a little bit. On the right hand side, I'll put in the actual mole of copper 2 carbonate, which is 0.5 gram, because they say they suspect all the 0.5 gram only contain copper 2 carbonate. So all of the 0.5 gram divided by the molar mass of copper 2 carbonate, there's only one thing present there, if the student was correct. The acid used was 0.500 mole per dm cube. Let the volume of the HCl be X cm cube. So they want the minimum volume in cm cube, so let that be x cm cube. So x cm cube, you gotta convert it to dm cube by dividing by 1000. So this is actual mole that reacts. This is from the mole ratio that reacts on the balance equation. So rearrange your equation. I move x up there. Then I get 0.5 over 123.5. I move up the 2. I move up the x, so it's x times 1, but I keep the rest of them down there. So this is a bit of rearrangement of equation, but it's nothing worse than your, I guess, primary school mathematics, I hope. Okay, so there's 16.19. There's to 4 sig fig. This data was given to 2 sig fig, but in terms of accuracy, we're looking at this being 3 sig fig. I think I'll be tempted to put down 3 significant figure for my final answer. But of course, I show it up to slightly higher significant figure before I round it up to the final option. Alright? But I mean, there's also 4 sig fig there, so 3 sig fig, 4 sig fig will be alright. I think if you put down 2 sig fig, there is too little. Okay, 16 cm cube and 16.2, there is quite a big difference, yeah, in the world of this analytical chemistry. Next up, you have azurite. So this is blue, and it's copper containing compound. Again, you have this, it looks like a mixture again. So it reacts with sulfuric acid according to this reaction shown. Now you do a series of titration. Okay. Excuse me. Any other material does not react with sulfuric acid, so only this thing reacts with sulfuric acid. You get copper to sulfate, you get CO2 and H2O. You get CO2 because there's carbonate present. You get the salt because there's carbonate reacting with acid. There's also the hydroxide reacting with acid. Alright? So you do a rough titration always, so that you know roughly when to stop, and you know roughly around 20 cm cube you would do drop by drop, and then you do them accurately. But this student hasn't done it very accurately. Only 2 titration, and these things are so far apart. You should always aim at plus minus 0.05 cm cube apart maximum. Even in your practical experiments, you know that you shouldn't have anything more than plus minus 0.05 cm cube for your exact titer. That's why we do a rough titer. Yeah, try not to be exact in a rough titer, because what is the point of being careful in a rough titer? Because you need to know when to stop. That's why you do a rough titer. Then you try to be careful in your first exact titer. Alright? But repeat as many times as you can in order to get consistent, reliable results. Okay? And try to do the exact same thing every time, so that you are not changing so many things at one time. Yeah. So the indicator for this titration was bromophenol blue. You have used it in your experiment before. The student concluded 24.15 cm cube of that sulfuric acid completely neutralized 1.50 gram of azurite. So we don't care whether the student is very good at titration or not, because frankly speaking, these 2 titers are so far apart. But the student has taken the average, and the student has gotten this average value. So they say you gotta use this student value of this titer. We gotta work out the percentage by mass of that copper compound in the sample azurite. We gotta write our answers to 3 significant figure. They give us the MR. If we look back at the equation, so the mole of the copper salt, I just write copper salt, I can't be bothered to write the whole formula, it's too long, yeah? Over the mole of the sulfuric acid is 1:3. As mentioned previously, you could have gotten it the other way around. You just do 3:1. Does not matter at all, because you know it is it is what you put in as the is what you put in on the right hand side as the exact value that matters more. So the copper salt that you used was 1.50 gram divided by 3 for 4.5. And then the acid that you used was, hang on. Why am I? Okay, hang on. So if I let the mass, let the theoretical mass, well, let the actual mass of the copper salt that reacted be Y. So I get Y gram of the azurite actually reacted. Then I get 24.15 times 10 to the minus 3 times 0.400. So work out the Y. So Y over 344. I'll try and do it in 2 steps so that you can see what is going on. But if you know what I'm talking about, you obviously could have done it in 1 step. You move all of this up there, divide by 3, and then you can move this up there, and then you multiply by 344.5. So Y is equal to 1.10929 gram. These are based on the equations. This is the actual amount of sulfuric acid that reacted. This is the actual mass of this thing that reacted, because the azurite is a blue copper containing mineral, but it can contain other substance as well. But the other material does not react with the acid. Only the copper compound reacts with the acid in this ratio. Yeah. So we work out the actual mass of the copper compound that reacted with the acid. All right. So this is the actual mass of the copper compound that contains this much. So therefore the percentage by mass of the copper salt, well, it's not exactly a copper salt, right? It's not exactly a copper salt, it's a copper compound, because salt would mean like you formed the sulfate already. So maybe I just go back and change the thing to copper compound, because salt is something like this, but this is not exactly a salt, it's still a carbonate and a hydroxide. So I just change it to compound, and we will get 1.10929 gram. That is out of 1.50 gram. Out of 1.50 gram, and gram, the 1 percentage, so the gram cancel out. I got 73.95. They also want it to 3 significant figure, so that is 74.0% to 3 significant figure. They did say 3 significant figure here, so don't get fooled by it, and don't make the mistake at the very last step as well, because they will cost you 1 marks. That doesn't look very nice. Let me just make it nicer. Okay, so there's just some easy 3 marks there. Identify 2 possible problems with the titration. How can you improve it? Well, one thing, as I mentioned previously, you see how the accurate titer was not consistent to this. Okay, so the titers, well, at least the accurate one, not the rough one, are not consistent and accurate within plus minus 0.05 cm cube. So all you could do is repeat the titration until consistent reading or consistent titer. Well, titer is a volume already, so consistent titer is reached. That is within plus minus 0.05 cm cube of another accurate titer. Okay, and the second one was, so you use an indicator, right? You use an indicator which is colored. Okay, so this indicator is colored and you will get color changes. But what is tricky about this compound is that this compound is also colored. Okay, this compound is also colored. Your indicator is also colored. So really, it's not a problem of the indicator, it's a problem of the compound being colored. So really, you know, the copper compound is blue, and hence have colored solution and hence have colored solutions. And remember that you are also forming copper 2 sulfate. If you know anything about copper 2 chemistry, copper 2 sulfate means copper H2O6 from your transition metal chemistry in A2. This thing is also pale blue in color. Okay, so pale blue in color as well. So you're producing something which is pale blue at the end. So not only the copper compound is blue, also the copper 2 sulfate aqueous containing copper with 6 water complex. So there's the aqua complex of copper 2 plus is also pale blue. So difficult to see color changes by the bromophenol blue indicator. I think I might have written way too much, but it's the problem of the color of the solution, whereas usually in a titration we have colorless solution, right? So it's just the color, the indicator that stands out. Okay, so use a different suitable indicator. So something that doesn't overlap with the color of the solution at all. Otherwise, it's very difficult to tell the endpoint. Okay.